Streaming is on. So, welcome back, and we are starting with another topic or another episode of Freud. So, in the last episode, we saw that they are navigating through the forest, through the trees, and they're kind of almost halfway there. So, they decide to climb one of the trees and check how far they're out. So, Freud climbs. So, this is going to be your cognitive check from the previous class. So, as usual, you guys have 1 minute. Talk. All right, I'll give you 2 minutes because this is going to be a lot of cognitive checks, not many. I think 1 minute should be a good time, but we'll still see. So when you're done, just hit a thumbs up so I'll know you guys are done, hasn't completed it. So yeah, okay. So help Freud climb the tree in his dream, because in Freud's actual interpretation, climbing a tree has a very sexual meaning, but nothing here, nothing sexual here. So try to climb the tree, or help Freud climb the tree. And of course, so you have to choose only the right branches, the branches with the right statements. Those branches which do not have the right statements will end up in Freud falling down. Want it falling down. You guys have 1 minute. Let me know when you guys have completed this puzzle. We'll move forward. Let's start now. So if you guys face any issues interacting with the slide, do let me know. You guys have completed. So anyway, I'm just taking out all the slides or all the branches which are wrong. I should also explain, right? So the first one said mean of any, the first false branch said mean of any distribution of scores when it's converted to Z distribution is always 1, which is false because Z has this formula. Z score equals to X minus X bar by your standard deviation. When your X is the mean, both will be the same. So you get same value, so it will be 0. Anything, if you divide 0 by anything, you'll still get 0. So that will be 0 for the mean value. So this is something that everyone should know. So therefore, mean of a distributed set of scores when it's converted to Z scores is 0. So here the branch said standard deviation is defined as the means of squares of deviation scores. So it is not standard deviation. That is, standard deviation is not. So standard deviation is actually the square root of what is mentioned here. So if you have deviation scores sum and square them, you divide it by the total n, you get variance first. And then if you take the square root, that is where you get standard deviation. So if you just have a sum of deviation scores squared divided by the total values or total number of data, have variance. Anyone has questions, thoughts so far? And quartile deviation is calculated as Q3 minus Q1 by 2. And number of quartiles is of course 3. So this is wrong. And mean is not the best measure for a very skewed distribution. Okay. So it will be median. So this is also wrong. And mode of a frequency distribution is usually the peak on the x-axis value. So this is y-axis, this is x-axis, this is a distribution. So this is your peak. Okay, so whatever value that corresponds to on your x-axis is your mode, right? So this is also true. So we had Freud reach the top, so we're going to take a look at what is out there from here. So they are seeing a lot of ghost-like shapes, which is kind of the normal distribution, or you could say paranormal distribution for fun. But anyway, so Freud asks, is this normal? Because he has never seen such things in his days when he studied psychology. And Raida answers, yeah, these are actually normal. These are also ghosts that have been haunting me so far. And apparently, or ironically, these are normal curves. Okay? So Freud reminds, if he dies, if Frida dies, he also dies. He reminds her to be careful. So we'll be discussing normal curves, and we'll be discussing certain calculations based on the normal curves. Lag has started again. This. So we have discussed about the Z scores, right? So if it follows a particular shape, move further again. If the Z scores follow a particular shape, or even the raw scores, the distribution is called a normal distribution. Okay. So it was first proposed or discovered by the French mathematician Abraham de Moivre. So it was not actually Gauss who discovered it. It was in 1733. So later, it was again discovered or rediscovered by two people. So the German that we know as of now, Carl Friedrich Gauss, and Gauss is also, sorry, I was supposed to say the normal curve is also called the Gaussian curve. So since this is just short, let me clear the topics for you, and then we'll go on to the more complicated one. So it was also at the same time rediscovered by Pierre Simon. Okay. So what Gauss did was he tried to plot the errors on graph, errors committed when you measure things. So the errors occurred in a particular distribution. So there are very few errors happen in a particular test by a single person. There are errors that are slightly more. There are errors that are kind of like the midpoint. They happen the most frequent. Is also your mode. And larger errors also mimicked the smaller errors, which were kind of decreasing in frequency. So therefore, he called this the normal law of error, not chance, error. Okay, so simultaneously, you guys can also try to unlock the slides. So this normal curve is actually not a normal law of nature, but it is only a law of error. So it is not a law of nature, right? So in the sense that you may find a lot of characteristics variables which are distributed like this, but there are also variables which are not distributed normally. So not every variable in nature or every real variable will be distributed according to the normal curve, right? So this normal curve has a function which we consider as f of x or y, right? So that is this formula, which is kind of quite lengthy, so you don't really have to memorize this. Okay. So if we take away this and this tail, it appears like some sort of a parabola, right? So parabola has f of x equals to x square formula, but you cannot take this formula as the normal curve form because you do have the tails. So therefore, it is different from what a parabola usually, because the parabola keeps extending down. So there is a mathematical abstraction for this, and this is the formula that is given here. But you really have to memorize that formula, I would say, right? Because you will not be asked about the exact formula, and it happens to be very lengthy. So any lengthy formulas you find in statistics, you could best assume that it's best length, right? So let's move forward. So you guys have another minute to unlock characteristics of normal curve, and these are the characters. So time starts now, and let me know when you have finished. So if you have teams, you can interact with the slides. If you're joining in action, you're watching from YouTube stream, obviously you cannot interact. Not loading. So we are in characteristic. If you had tried to switch slides by yourself earlier or way before we started, so try syncing to the presenter's view. Can everyone see characteristics? Turn off the camera. It's faster for. All right. So if you guys are finished, let me tell you. So there are certain characteristics for all normal curves. Okay. All normal curves, they are symmetrical. So you can easily see here. So these are normal curve. This is a normal curve, so it is symmetrical. So symmetry is one of the most important characteristics. You have a curve or a distribution that is not symmetrical, so it is not a normal curve. So in case you have a asymmetric curve, so it is supposed to be skewed. For some reason, not good. Okay. Oh, okay. It was supposed to be symmetrical. It is switched. So systematic is not the right answer. It is symmetrical. Okay. So all normal curves are symmetrical, and they are unimodal distribution. So mode is a single value, right? So when you talk about normal curve, there is only one peak. So you do not have 3 or 4 or 5 peaks. Okay. So if you have several peaks, so they are all modes. So mode is literally the highest occurring value. So there should ideally be only one single highest occurring value in x-axis. That is your mode. So normal curve usually always has one, or not usually, will always have one single mode, which we call as unimodal, right? And you can also see mean, median, mode are literally the same line. That is another characteristic. Okay. So when you're asked about characteristics, you'll have to remember these, and so you can be asked the or MCQ. Starting at the center of the curve, if you move outward, either on the left or right, the height quickly descends. So height quickly decreases. So height is the most at the peak or at the center. Okay. And it quickly descends, and then it slows down. So actually gradually descends for a while, okay, and then it suddenly decreases very fast, and then it is again slow. So this is another characteristic. So this is not something you will be asked in terms of or something, but these parts are actually very crucial. Right? So these are called the tails. So in a normal curve, in an ideal normal curve, these do not the x-axis. So you see here, this is the x-axis, and the one in the black is the normal curve. It doesn't actually touch the x-axis. The idea is that there can be one value or more values which is lesser than what we have recorded so far. Okay. So maybe in your data collection, this is the range of data on x-axis. There could possibly some value if you extend your sample, that could be even more. So that is the reason normal curve never reaches x-axis, or the frequency of that value never actually reaches 0. That is how we keep it. So such a curve is therefore called asymptotic. So it is not asymptomatic. So that would mean you don't have any symptoms. So this is called asymptotic. The normal curve is continuous distribution. So even if you flip coins several times, you will get somewhat similar to a normal curve, but we will not consider that a normal curve if you just have head or tails, okay, because that is bimodal distribution. A true normal curve is what applies to a continuous distribution. Let's go back earlier slide. And there are certain set of proportions for a normal curve. So if you talk about, let's say, in terms of z scores, 1 standard deviation to -1 standard deviation, yes, you'll have a set percentage of values that are present. Similarly, -2 to +2, you will have a certain set of values. Same for -3 to +3. So this is same for all normal curves, right? So you can also say the peakedness is the same for most normal curves, and obviously the skewness is 0. So the peakedness of all normal curves are or is close to 3. Okay. So anything that is lesser than 3 would be platykurtic, or more than 3 would be or leptokurtic. It is very, very peaked. Now, a quick question. T distributions, right? So what type of kurtosis do you expect for a T distribution? The lepto, meso, or platy? So if you're listening, let me know what is a T distribution. So what is a distribution for a T? What is the kurtosis? Leptokurtic. So does anyone know the reason for it? Does anyone know why is a T distribution very peaked compared to a normal curve? Quick thoughts, anything, like take guesses. Seconds, I'll reveal the answer, but let's see if we can guess. Why is a T distribution very peaked or leptokurtic? This can arrive as a assertion reason question. Yeah, the distribution is smaller, so therefore what? It is still not the reason. So small sample, yeah, it's a correlate of why T distributions are small, but what happens when you have a small sample? So what will happen if you have a very small sample? Okay, that is also a good way to say less variation. In other words, your chances of getting extreme scores is very less. I would not say they usually gather around the mean as a rule, because that happens when you increase sample sizes. A T distribution may be slightly skewed also, which is not ideal, but it can happen when you have very small samples. So a T distribution is very similar to a, what do you call it, normal curve, but it is more peaked, because of course if you see or draw samples from, let's say, this, we consider as a population, if you draw samples from this, if you just draw 10, okay, so chances of you getting 10 are most high here, because 50% of the cases lie here. And if you increase to 1 standard deviation, you get 68% of the cases in this area. And if you have, let's say, 2 standard deviations from here to here, 95% of the cases are lying here. So to get some things very extreme, you just have less than 5%. That is the more than sign. So you'll have something less than 5%. So if you have a small sample size like 10, the chance of you getting very extreme numbers are almost, I'm saying almost. Okay. So that is why you will not get something on extreme. It is going to look more peaked than it actually is. So the tails will be very, very, very thin and they might retract. It will become like this. That is why it's more peaked. Okay. So as you increase sample size, your variation also increases, and therefore the tails get slightly thicker and you get something like a normal curve. But to keep increasing the sample size, it will not get platykurtic. Okay. Because for you to get a platykurtic distribution, you need to get more extreme cases compared to the in between, which is very unlikely again. Some people may think or have asked in previous classes. So if you keep increasing sample size, does it mean it becomes platykurtic? Kind of retains the mesokurtic shape. Right? So any other doubts, questions before we move forward? Is it all clear? No other thoughts? All right. So you guys have another minute to unlock this, or maybe just 30 seconds. So you have 3 locations to unlock. So this is what I was saying about the area under the normal curve. Okay. So you guys have 30 seconds and let me know if you have unlocked. 30 seconds are up. Anyone finished? All right. So if you're supposed to use normal curve as a representation or a model, so we literally kind of convert it to Z score or a standard score distribution. Because when you have normal curve based on raw scores, so the x-axis is literally your raw data. So it will be 0, 1, 2, 3, 4, and so forth. So if you compare two normal curves, it is very difficult to communicate. First, you need to know what is the range of your distribution. Okay? And then you will have to tell them what is the mean and so forth. So it is better to tell people after converting into Z score, because when you convert to Z score, the mean is always okay, and standard deviation of a Z score is so what is the standard deviation of a Z score or Z distribution? So we know mean is 0. So what is the standard deviation of a Z distribution? 1 SD, right? Okay, good. So you don't really have to tell people my mean of the distribution is 0 and 1, because everyone knows if it is a Z distribution, that is the case. Okay. But if you have a raw score, you will have to literally tell people the mean, what is the SD, what is the minimum and maximum scores, and so forth. Right? It's tedious. That is why to communicate or to use it as a representation or a model, it's best to convert normal curve with raw data to Z, our standards. Right. So now the shape of normal curves are most approximately similar, right? So it's a bell-shaped curve with very slim tails, and most of the scores lie in the center. So if you consider one quartile to the third quartile. So the quartiles are these. So this and this are the three quartiles. Okay. So you have approximately 50% cases here. The remaining 25 and 25 are here. Okay. So considering IQ, your 90 to 110, which is considered the exact average value, is this 50%. Right? So 50% of the cases lie between quartile 1 and quartile 3. You see that there's a very slim range. Right? So beyond that is still quite a lot of areas. So if we consider one standard deviation on the negative till the positive side, there are 68% cases. You literally have to remember this so that you can calculate problems based on this. And from two standard deviations on the negative side to the positive side, you have 95% of cases, or approximately 95% of cases, or I would say just slightly more than 95% cases. But for purpose of calculations, let's keep it as 90. It's just slightly more than that. We'll just keep it as 95 for now. And between -3 to +3, we have 99.7% cases. These are statistics supposed to remember so that you can calculate more. So I guess ready to solve problems based on this. It's going to get very complex very quick. Any other doubts, questions before we go forward? So we're going to solve three types of problems. One is to find the percentile. So which means literally the percentage of people below a particular point. Okay, that is what is called percentile. Even at a particular point, from here till here. So what percentage of population present? So that is your percentile. So we'll also be finding area between a particular range. That is the area under the curve. Or you may be given a percentile and you will be asked to convert that into a z-score or raw score. Right? So are you guys ready? Do you remember these? If so, we can start. Hope so. So we're going. So you guys can unlock the slide and try to answer stuff, but I'll also be explaining along the same. Okay. So first one is finding areas when the score is known as in what percentage of people lie below or above. That is what we're going to do. So here we are given a particular sample description. So the descriptive statistics of this particular distribution is we have a mean of 100 and a standard deviation of 20. So this is SD, 20 is SD, and SD equals 20 and your mean equals 100. So this is likely to be some sort of an IQ test with a very wide variance. So that is why instead of 15, you have 100. So let's consider these descriptive statistics. So what they're asking is your score, what mean? You gotten a score of 120 or someone got a score of 120. So what percentage of population lies below it? Okay, so that is what we are supposed to calculate. The first step is to calculate the z-score. You are supposed to turn this into a z-score, right? So how do we turn this into z-score? You use the formula z equals x minus x bar divided by your standard deviation. So someone already answered it. So for the sake of others, we'll be waiting. Okay. SD is 20, so let's put 20 here. So the value that you're finding is 120, that is your x. And of course, x bar is your mean, is already given is 100, 120. Write it wrong. So you have 20 on the numerator and 20 on the denominator. Okay, so because 120 minus 100 is 20, 20 is in the denominator, so z becomes plus 1. So the sign is actually pretty important. So you may be like, how do we go forward now? So plus 1 is like literally here. So what do I do right now? So we know something. Minus 1 to plus 1, we have 68% case. Okay. The area from here to here is 68%. So what we want is, what proportion of cases will fall above in this location? Okay. So there are several ways to go about it. So, but all of it requires us to split this area in half. So if this much is 68, what is the distance from the mean till 1 SD? So from minus 1 to plus 1, you have 68% cases. So from the mean till 1 SD, it is half of it, 34%. So you have 34% in this gap. Okay. So we know that the midpoint splits the whole distribution into two equal halves, which is 50-50. Okay. So if this whole thing is 50 and this much is 34, what will be this? Note that this is 34% and this entire right hand side is 50%. So what is the proportion of scores above your 1 SD? So that is for you to calculate, and let me recap. So the Z value is plus 1, what we have calculated, and we know that 50% of cases lie from the midpoint on either side. So if we consider just one side, it is 34% of the shaded region. I'm asking, okay, so 84% would be the percentile. So what I've asked is, what proportion of cases fall above 120? So we are literally checking this region. 84% would not be the right answer. So we literally need this. So instead of adding 50 plus 34, we subtract 34 from 50. Okay. So when you consider from minus 1 to plus 1, it is 68%, and half of it is 34%. Right? So from 0 till minus 1, you have 34%. And from 0 till the maximum value, you have 50%, because that is how the midpoint works. Okay, so we need the remaining. So we subtract 34% from the 50. Are you guys following? That is how you get 15%. But if we talk about below that point, which is a percentile, you will get 84%. You will have to add both of it. So why do we add both? So this was for above this point, above the set point, which is 120. Till here is 34. Till here is 50. So we just subtracted 34 from 50. We got 16. I hope everything is clear so far regarding this. You know, back. So, but what if someone asks you the percentile at 120? So you literally have to find out the amount of scores up till this point, because 120 we have already calculated as plus 1 SD. And we already know minus 1 to plus 1 is 68. And if we divide it by 2, we have 50% on either side totally. And from 0 to minus 1, we have 34%. So we literally want this whole 50% and plus whatever this is. And whatever this is 34. We just have to add 50 and 34 for calculating percentile for 1 SD. That is as simple as that. But if you want this proportion, you have to subtract 34 from 50. That is how you get. That is the answer here. It might sound complicated, but it is actually very, very simple. Can we try another problem where we try to calculate limits? Maybe finding the score when percentage is given. Any doubts, questions before we move forward? Can we go forward? All clear? Are of course going forward. So you're going to find the score, the raw score, when the area is given, right? So we are given a particular problem here. You guys can also unlock the slides while I try this. So the problem is same IQ test. The mean is 100. Talking about this. And the standard deviation is 16. So earlier we were given 20. Now we are given 16. So Binet scales used to have 16 as standard deviation. So that is one more fun fact for you. So the percentile is also given, which is 97.5 percentile. So we are asked, what is the score that corresponds to this percentile? Suppose if we use this post as the normal curve, this is the midpoint, which is mean, median, and mode, right? So from here till, let's say, a particular point is 97.5% of the case. Okay. So they're asking, what is this point? So the first step again is to identify your Z score of it. But to do that, you'll have to do some gymnastics, mathematical gymnastics. Okay. I hate it when it just changes. Okay. So yeah, the first step is to find the Z score corresponding to this proportion. But you guys know, we are not talking about something symmetric here. So we're not talking about this point negatively to this point positively. Okay. So we are talking about from absolute beginning of the score till a particular point is your percentage of scores, which is your percentile. So we need to find out what is this so that we can get a symmetric value and then compare it with what we already know. Okay. So we can split this whole 97.5 into 50% plus 47.5%. How? Because the midpoint splits the entire distribution into two equal halves. The left half is 50%. This is 50%. If you subtract 50% from this overall, so you remain with 47.5%. Hope you guys are clear so far. So this is 47.5%. And now if you double it, let me ask, why are we doubling it? Because we need to know the range from a particular location till this point, which is symmetrical around the mean. That is how we will say, oh, this happens to be some sort of this Z. Okay. So 47.5 is here and another 47.5 is here. That would mean we have a total of 95% rounding the mean if we have this as the point of reference and if it is symmetric around the mean. And obviously we know 95% of the cases are between -2 to plus 2 standard deviation. Where is this given? So it was given way earlier, 2 slides back. Or you can see even in this slide, 95% cases lie between -2 and +2 standard deviation. So that is how someone in the chat has arrived at +2. So 97.5 percentile corresponds to +2 standard deviation. Now we are supposed to find what is this +2 standard deviation. This is actually your Z score, because all the X values on a Z distribution is a Z score. So from now on, it is pretty easy. You just have to apply Z score formula and figure out what is the corresponding raw score. So same Z score formula, Z X minus X bar divided by SD. So we know that SD is 16. Put 16 here. X is something unknown to us. We keep it as X. And X bar is 100, which was given before. That is something we've also figured out. +2. Z and 2 kind of are very similar in appearance. So I2 might look like Z for you. Anyway, so you just bring into this side. So this becomes 32. Right? So now to find X, you just have to bring 100 to the other side. It becomes plus, so it will become 132. Can you hear me? So the X value that corresponds to 97.5 percentile and 32. And 134. It should be 132 because we are considering 2 standard deviations. One standard deviation is 30. One standard deviation is 16. It is 130. Hope you got the logic. Okay. So this is how we calculated 100 plus 132 is how we got it. 95% of the cases around the mean in terms of Z scores is plus or minus 2 SD on the lower and upper limit. So we did the half and then did the twice as multiplied 47.5 was to get a range around the mean. That is how we know so many percentage of cases lie. Sorry, this should be 95. Options were kind of wrong. So if you consider 84th percentile, so which is literally 1 standard deviation above the mean, and your IQ will be 116 in the same scenario. And for 99.85th percentile, which is the 3rd standard deviation, you will have a score of 148 because 3 standard deviations above the mean. 3 into 16 is 48. You just add 100 to it, you get 148. I know the last one may have been complex for some people, but if you try out this problem, you would easily understand. So anyone has questions in this? All clear? We'll look at one other type of problem that we found. This might be the most complex, and whatever is left out and what we saw earlier are actually most simpler. So anyway, we are moving forward. So let us find the limit. So what we did earlier, we found -2 and +2 as having 95% of the cases. Okay. That is also what we will be doing right now. Sorry, that was supposed to be plus. So you have to find the limit within which a certain percentage of score fall. find the upper limits of 68% of cases. Find the upper and lower limits for 68% of cases around the mean. So we know that for 68% cases, the range is -1 to +1 standard deviation. For some reason minus is involved. 1 and +1 standard deviation. Okay. So what is -1 in terms of raw score? You just put it in the Z formula. So Z is 1, and on the other side, the Z is 1. On the other side, you have X minus X bar by whatever standard deviation. Okay. Suppose we took 16 and X bar was 100. So the lower limit becomes 16 . So this will be the upper limit because we're talking about +1 standard deviation, right? So when this comes to this side, this will become 116. The upper limit for 68% cases will be 160. So if we had lower limit, you would have started with -1 Z score instead of +1. Right? And 16 would have gone here, it would have become -60. And 100 would have been added here on the other side. So it would have been 100 minus 60. So you'd have gotten 84. This would have been 84 or 68% of the cases around the mean. So similarly, you could do for 2 standard deviations. So you'd have gotten 1 standard deviation is 84, you would have gotten 68. Okay, and you would have gotten 132 here. For some reason my stylus is lagging quite a lot. Let's see if we get 60 written on the screen. Right. So if we had 15 as your standard deviation, tell me what would be the lower limit for -2 standard deviations and +2 standard deviations? And similarly, what would be the upper limit for +2 standard deviation? When you have standard deviation as 15 and same mean is 100, standard deviation as I said 15, what would be the lower limit and upper limit from -2 and +2? 70 to 130. And another fact, so this happens to be the non-disabled range. Okay, 70 to 130 is a non-disabled range in terms of IQ. So -2 would be 70, +2 would be 130. So anything less than 70 is considered as disability to test. 70 to another 1 standard deviation. If we are talking about 50, be how much? 70 to another 1 standard deviation is considered mild disability. What is that range? You know what I'm doing. So 70 is the starting point, or 69 would be the starting point for disability. So up till what range is mild disability? 1 standard deviation is that next limit, or the next 1 standard deviation should be -2 SD. 70 to what range is mild IDD according to a IQ test? 40. So just subtract 15 from 70, right? So another standard deviation is what you're supposed to subtract, right? You subtract 15 from 17, it'll be 55. So according to an IQ test, 55 till 69 would be your mild SD. Okay? So now, what would be moderate? So it will be 54. Anything less than 55 will be considered as moderate. Till what? So another 15 is supposed to be subtracted because that is 1 SD. 54 till 30 would be your moderate IDD. So beyond that, we consider as severe and profound, but it is very difficult to distinguish between severe and profound using an IQ test. There we might use something in addition, which is your adaptive behavior scale, because IQ test, as we discussed in the last, is an interval level measurement. So on the very lower ends, it gets very, let's say, insensitive. It's not very sensitive to gradation. All right. So that's about this. We've already sorted, so I think unlocking this slide kind of not a great deal. So I'll just quickly unlock this. So we did 100 minus 16 to find out the lower limit. So lower limit 100 minus 16 would be or 84, and hence 68% between 116 and 84, or otherwise 84 and 116. So we're done with the most of the calculations. Any doubts or questions you guys have for now? If you do, I can answer those. Thoughts, questions, doubts? All? None? We'll just look at this last slide. Then we'll meet again tomorrow. So there's a surprise for tomorrow, which is kind of more of a challenge. But yeah, we can do that. Anyway, so the normal curve is not only for calculating these percentiles, areas, and the limits. It is also used in inferential statistics. So it is considered a model for sampling distribution, especially for variables which are tended, assumed to be normally distributed in the population. So consider this: you have a population, and the population is normally distributed. So you draw, say, 100 samples from this population. So some of your samples may be lying here in terms of their mean value. This. So some of the samples may be lying here in terms of their mean value. Some of the samples may be lying here. Some of the samples may be lying here. Some here. Some here. Some here. Like so many, like the. Okay. If you build another distribution based on the mean values of all these samples, that will also be another normal. Okay. So all possible sample means from a population will also be a normal curve. So this is how we test for mean differences using t-test, or if it is normal, z-test. So in this case, we use some sort of a critical region. We'll talk about that in the next class. And anything outside the critical region is considered some sort of an error or data away from the mean. So why do we call those errors? Because you have a mean value, and anything surrounding this mean value is acceptable as a representation of the population. Anything too extreme may be considered not belonging to the population. That is how we test for hypothesis. What our next topic is. Okay, so you guys have 30 seconds to unlock this slide. Again, you can use whatever instructions, discussions I have given you. You have 30 seconds. Let me know when you have unlocked. have 4 blocks in. Okay, so it's already 30 seconds. Okay, has anyone unlocked this all? So normal curve is also a function, also functions as a model. So we already seen that for sample statistics. So when we talk about mean median mode for the sample, we call it statistics, and the same median mode for your population called a parameter. We'll be discussing this again when we talk about hypothesis. So if you draw a lot of samples from your population, great number, like almost an infinite number, okay, and each sample has the same size. We're talking about sample having each same size and compute means of all the samples. Okay, so this mean distribution of various samples will also kind of be a normal curve as we have seen, right? So for this type of distribution, the normal curve will be a very good representation. So this is based on how we will test whether your sample, which you have drawn from a particular population, is representative of population or not. If it is not representative, that is how we hypothesize and say it is significantly different from your population. That is what we do in hypothesis testing. We can test hypothesis around the means for one population and the sample or two different samples. Got it? So this is what we'll be looking at as T test or Z test. But before that, we need to understand the logic of hypothesis testing, which we'll do in next class. For now, this may have been a lot because there are quite a lot of statistics that were involved. So our characters, Freud and Frida, they kind of are still in the dreamscape. Frida has not awake. And now they have two paths. So they're supposed to decide which is the right path. So and the ghosts just mock them by saying, why don't you hypothesize and find? So we'll figure this out in the next class. We'll have a lot of cognitive checks based on what you have seen. There's going to be a lot of sums and problems. So any doubts, questions so far, we can discuss. Oh yeah, tomorrow we don't have a class. Okay, I could not open YouTube and sorry, I could open YouTube, but I could not open WhatsApp on my desktop. So that is the reason I have not shared it. So, but the recording will be available by tomorrow morning. Okay, so we'll have the recording by morning and you can check that out. So tomorrow we'll have something called the Fight Club. Will be one of the very few instances where you guys can participate in it, as in it's open for all. But then it later it will be only open for those who have been part of the paid subscription, right? So what we'll do is we'll do something similar. Let me show so that you can out. So you guys know the Jamboard or the whiteboard, right? So what I'll do is I'll create true or false statements on the whiteboard. You guys can also do the same, but I'll not tell you which is true, which is false. So you guys will not also tell me which is true, which is false. So each one of you will have some sort of an island. So each person then will go around after a set time and identify the true or false state. Thing like this. Okay. So whomsoever's true or false statements are the least identifiable. Then if a lot of people have identified your false statements as false, true statements as true, then you, which is something you will have to reveal after a particular time. So whomsoever's true or false statements are the least identified. So they will be kind of the winner. Hopefully, you guys won't be able to win. That is what I'm hoping. So we have this fun activity for tomorrow. So let's see if you guys can join tomorrow. I know not many people do join. Timing will be the same, 7 p.m. And do read up on whatever we've discussed so far. So if you have our notes, it'll be very easy for you. Otherwise, you just use Erlinger and you can also use Howell. PC Howell, PC only, no? So both are like pretty good books. So that's it for now. See you guys tomorrow, and it'll be the same time. And if you're on YouTube, you can always join the WhatsApp group to get these links and actually interact with the PP. That's it. See you guys on the next episode or next. Yeah, as you can see, you can all so, but you will be given a single notepad where you'll be writing true or false state. And then using reaction, and just put tick or wrong just next to a state. That is how it will work. Anyway, so we'll do this tomorrow.